Hey guys, so welcome to class. Obviously a little bit different than what you're used to, but for today's class we are focusing on two new concepts. One is that of discontinuity and the other one is continuity. We will obviously not have a video for your work time, so go ahead and after you do this lesson, turn to Delta Math, work on those assignments, and then I recommend that you do the Delta Math first, then the exit ticket. That is for today's class. So the first thing that we are going to talk about is types of discontinuities. Now stop, wait a minute. Before we do that, we need to talk about a concept called limits. Limits is really cool because it is actually the basis of all calculus. We like to teach this lesson, or I like to teach this lesson during the end of the school year so that it's fresh for your mind in case you're interested in taking calculus. It will build a strong foundation for you. So limit is different than output. When you have input and output, that is the exact value of a function once you put in a specific input. A limit, the key of a limit is more about what a function approaches than what that function actually equals. So it's what output is this function approaching as my input approaches a certain value. So in other words, it tells you the y value of a function as the y value that a function approaches as the input of the x value gets closer and closer to a given number. So for example, we're going to keep it real simple and start with a quadratic equation. I could ask you, what is the limit for this graphed function as x approaches 2? So when you're looking at the limit, you want to see what the graph is approaching from both directions. So what that means is I want to evaluate it from the left, but also from the right. So imagine I'm literally on this graph. Like I'm on a roller coaster that is parabola shaped. As I'm approaching 2 from the left, what output value am I approaching? You can see as I get closer and closer to 2, I'm approaching a y value of -1. Now you want to do the same thing from the right. So from the positive direction, I'm going, I'm getting closer and closer to my intended input of 2, and I'm approaching -1. So my limit as x approaches 2 would in fact be -1. Now, the way that you tell the difference between discontinuities is by using limits. So there's 3 types of discontinuity. You can see them on the screen. You can see there's removable, and then there's jump, and then there's infinite. So let's start with removable. Removable should look familiar. A lot of holes on the rational functions we learned at the beginning of the semester is removable. There's just an empty hole and then an empty hole that has another point filled in. Those are both removable discontinuities because when the limit from the left, you want it to also equal the limit from the right, but the actual value will either be undefined or equal another value. So I'll show you an example of what we mean by that. But you can also think of a removable discontinuity as something that you can just eliminate real quick by like filling in the hole or moving the output. So this question is asking you to find all values of x in which there is a removable discontinuity. There is going to be one at 4 because you can see that hole. And the reason why there is one is because as you're approaching 4 from the left-hand side, you can see it's approaching a specific number. As I'm on this graph, I'm going, I'm approaching 4, you can see that it's approaching a value of 0, right? And from the right, I'm approaching 4. It's still approaching 0 from the right as well. The only thing is that if I asked you for f of 4, your output wouldn't be 0 because it's undefined there, but its limit is 0. So limits are about what something is approaching, and output is what that output is at a specific input. Now, if I had said, okay, this is an empty circle, let me clear everything out, and I actually have a coordinate point at 4, this would also be a removable discontinuity, except for the only thing that changes is that its output would now be 6 instead of being undefined. But its removable discontinuity would still exist at, once again, x equals 4. So now I would go ahead and pause the video, answer this question. So you see a lot going on this graph. They're not always going to be as simple as the one I said. Pause the video and determine all x values that have a removable discontinuity. All right, so you should have at least tried to figure out what those values are. The removable discontinuities are in 4 locations. So I'm gonna move this over. Oh, okay, it's gonna be at -5. I see one at -3. I see one at 4, and I see one at 6. Now you might have been tempted to identify like -6 as one. However, that is a different type of discontinuity because the limit isn't approaching the same thing from both sides. So we'll talk about that a little bit more, but you should see that there is a hole here, 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 and here. Okay, let's talk about jump now. So jump is quite similar to removable, except for that the limit approaches different values from 2 different sides. And there's no like asymptote to deal with because that would be infinite. So let's say it's really easy to spot jump because think like if you were in a video game, like imagine we're in Super Mario Brothers, old school, and Mario was like running. If he went up here, he would have to pull some kind of trick to go down to this next level unit. He'd have to use a rope, he would have to bounce on a turtle's back, like he would have to find a way to jump from one point to another. The more technical math idea is that this value, if let's just say limit as x approaches -6, it's approaching 2 different outputs. So from the left, it's approaching 1, but from the right, as I get closer and closer and closer to -6, my value is approaching -3. That means that it's a jump. So I have a couple of jumps on this one. I have one at -6 and I have one at 5. It wouldn't be 4 though, because 4, it's still approaching the same exact value. This is just a hole. Same with that 0. So let's do the same thing. I'm gonna pause right here, or you're gonna actually pause right here and answer this question. So identify all x values that have a jump discontinuity. Okay, so hopefully you did that. Your jump discontinuities are gonna be at -5, +1, and +6. Last but not least, infinite discontinuity. That is when there's a vertical asymptote at a particular x value. So remember when we talked about asymptotes and holes in rational functions, same exact idea. Infinite discontinuities means that something will be discontinuous or undefined infinitely. It will never be defined at that specific point. Because remember, that's how asymptotes act. Asymptotes are imaginary lines that your function will get close to but never cross. So if you ever see this kind of movement around a function, you see the arrows, it shows you that it's going on forever, that means that it is an infinite discontinuity. So I see one at -3, but +2 is also 1. They're going in different directions, but it's the same idea. Last task is to do just the same thing. For what values of x are there infinite discontinuities? So pause it right here. And now you're going to get the answer. It is just at 3. So there's a lot going on, but these all on the left side of the graph, these are all the other 2 types of discontinuities. We're just talking about infinite. So that would just be at 3. If you are a note taker, which I really sure do hope you are, this is a great thing to put into your notes. So this is how you can distinguish and identify removable discontinuities versus a jump versus an infinite discontinuity. So pause right here and take that down. Moving forward, question for everyone. So the first person in the class period to text me the answer to this question will get a section of their Delta Math excused. So go ahead and answer this question, label it A, B, C, or D, and just give me the correct answer choice, and you will get a section of Delta Math excused. Cool, moving on. Second half of this lesson is going to be regarding continuity. I hope you enjoy these jokes. These are from my last year's slides. Continuity is the idea that a function has to approach the same value from both sides as the input approaches that boundary. So very similar language to what a limit is. The idea here is that continuity is a function that continues moving and without any kind of discontinuity. So these two graphs that you see are both examples of continuous functions. Oh, I don't have examples of discontinuous ones, but those are ones with holes, with jumps, with infinite discontinuities, right? So let's go ahead and talk a little bit about the anatomy of limits. This is the notation that you use. This will not be on any kind of assessment for pre-calc, but it will definitely be in any higher level math that you do, especially calculus or any variation of that. So you've seen me use this notation right here, limit as x approaches a value, then you would define the function here, and then this is what you want to think about, okay, what y value is my function approaching? So that's how you would use it. Now you might have noticed me also say something about left and right. I'm gonna zoom in a lot. You can see that the right and the left is determined by like the little plus and the minus sign by the value. So if I was saying what is the limit as x approaches 2 from the right, I would just put a plus sign next to it, and then if I want to compare what's happening on the left, I would put a minus. Those are pretty universal ideas of left and right. Okay, let's go ahead and move on. So now we're going to talk about some examples. So I've given you a lot of like figurative ideas, but let's do some more literal ones. So for a function to be continuous, it has to equal the same thing. It has to approach the same value from both sides. So this is a piecewise function that's giving you two sides of 2, right? So when you're plugging in, you want to plug in 2 into both of these equations to make sure that it's approaching the same output from the right side, so when all x values are greater than 2, and from the left side, when all x values are less than or equal to 2. So what I'm going to do is I'm going to plug in 2 into both of these equations to ensure that the output would approach the same value. So in the case of my right-hand side, I would get 24. In the case of my left-hand side, I would also get 24. Because they are equal to each other, then yes, they would indeed be continuous at x equals 2. Moving on. Go ahead and pause the video here. Let's determine whether the function is continuous. And then I will go ahead and show the work right now. So unpause it when you're ready. So you're plugging in, you don't plug in what it gives you in the domain, you're plugging in the value that it gives you. You want to test that specific value. So I'm going to plug in 3 into both of these equations to ensure that it is approaching the same value from both sides. So remember, remember PEMDAS, you got to square the 3 first, multiply it by 2, and then 7 minus that would give you negative 11. And then negative 6 minus 3 would give you negative 9. So negative 11 does not equal negative 9, so this one would be discontinuous. That's how you determine continuity. So this is the exact amount of work you need to show. You need to show yourself plugging in the 3 and then determining whether it's continuous or not. Delta math is a little tricky in this section. It's going to be a little bit interesting. So if you get a situation like this looks very similar to the last 2 problems, but if you look at it, if you plug in negative 4, there is no situation in which your domain equals negative 4. These are both like empty circles if we were to graph them. That automatically means that it's discontinuous because there's already a gap at negative 4. There's only values that are valid less than or greater than 4. If you're a visual, this is a visual representation of that equation I just showed you. You see that at negative 4, they're both empty circles, so there's already a gap here, a discontinuity, so it would immediately be discontinuous. The last scenario, kind of trick question that you would get is that you would get an input that is different than the actual boundary of the domains. So first, think about where would negative 4 fall into. Would it fall into the first equation or the second equation? You might realize that negative 4 would fall into this first equation because negative 4 is less than 4. If it's not at the boundary of that domain and it contains it, it's automatically going to be continuous. You don't have to test anything because you only need to test it if it's at the value that it gives you is at the boundary of the 2 domains. So that is automatically continuous. Folks, you have some homework to complete at this point. This one will be due on the 25th for all of my classes, so be sure to get on that. That is going into the grade book. And your final review is actually out, so go ahead and pick that up. I will set up a pickup date next week, and the final review is due for everybody regardless of whether you are exempt or not. Go ahead and once you are ready, log on to the exit ticket. I will share the password when it is time. Love you guys so much. I hope you are doing well on this Friday morning or afternoon. I will see y'all next week.